Thomson. The course of Pasteur's scientific work is one of remarkably natural and logical sequence. As the veteran Monsieur Chevreul long ago said in the Academy of Sciences, it is by first examining in their chronological order the researches of Monsieur Pasteur and then considering them as a whole that we appreciate the rigor of his conclusions and the perspicacity of a mind which, strong in the truths which it has already discovered to the establishment of what is new. We shall therefore summarize the record of his greatest achievements. As was natural in the pupil of Dumas, Balard and de la Fosse, Pasteur's first important piece of work was chemical and crystallographic, and we may best understand its spirit by recalling the work of de la Fosse's master in mineralogy, the Abbé Hauy, who is still remembered for that bold attempt to visualize the ultimate structure of the crystal, to penetrate the inmost secret of its architecture, which also reappears in another way in the work of Mendeleev. Pasteur's puzzle concerned the tartrates and paratartrates of soda and ammonia. These two salts are alike in chemical composition, in crystalline form, in specific gravity, and so on, but they differ in behavior. Thus, as Biot had shown, a solution of tartrate deflects the plane of polarized light passed through it, while a solution of the paratartrate does not. The salts are the same, yet they behave differently. A note to the Academy from the famous chemist Mitscherlich emphasized the entire similarity of the two salts, and this acted as an additional stimulus to Pasteur. He succeeded in distinguishing the minute facets which even Mitscherlich had missed. He proved that the paratartrate is a combination of a left-handed and a right-handed tartrate, and did much else which only the expert chemist could duly explain. Biot was first doubtful, then delighted. Arago, who had also busied himself with these matters, moved that Pasteur's paper be printed in the memoirs of the Academy, and Mitscherlich himself congratulated the young discoverer who had tripped him up. Already then, in this minute and laborious piece of work, we may detect ultramicroscopic mental vision, and that rigorous accuracy so characteristic of the man. Yet it is interesting to observe that at this early stage he was sowing his wild oats of speculation. Impressed by the strange rotation of the plane of polarization exhibited by these organic salts, he deduced therefrom a hypothesis of molecular dissymmetry, and hazarded the view that this was a fundamental distinction between the organic and the inorganic. For various reasons, neither chemist nor biologist would nowadays accept this distinction, but it is hard to tell what Pasteur might have made of this inquiry had not circumstances, regretted at the time, directed his attention to very different subjects. Being thus known in connection with tartrate, Pasteur was one day consulted, so the story goes, by a German manufacturer of chemicals, who was puzzled by the fermentation of his commercial tartrate of lime, which contained some admixture of organic impurities. Pasteur undertook to look into the matter, and probably deriving some hint from the previous work of Quenat-Latour and Schwann, who had demonstrated the yeast plant which causes alcoholic fermentation, he demonstrated the microorganism which fermented the tartrate of lime. He extended this discovery to other tartrates, and made the neat experiment of showing how the common blue mold, Penicillium glaucum, sown in paratartrate of ammonia, uses up all the right-handed tartrate and leaves the left-handed salt alone, its identical chemical composition notwithstanding. These and similar inquiries led him to tackle the whole question of fermentation, but his transference to Lille had probably much to do with this. For, as one of the chief industries of the district is making alcohol from beetroot and grain, Pasteur's practical sense led him to devote some of his lectures to fermentation, here, as always, as his biographer reminds us, wishful to make himself directly useful to his hearers. The prevalent theory of fermentation before Pasteur took the subject in hand was that of Willis and Stahl, revised and elaborated by Liebig. According to this theory, nitrogenous substances in a state of decomposition upset the molecular equilibrium of fermentable matter with which they are in contact. What Pasteur did was to show that lactic, butyric, acetic and some other fermentations were due to the vital activity of microorganisms. Then Pasteur carried his point, and although some of his detailed interpretations have since been revised, it is universally admitted that he changed the whole complexion of the fermentation problem. It must, of course, be borne in mind that his theory of the vital nature of many fermentations does not apply to soluble ferments or enzymes, such as diastase and pepsin, which are chemical substances, not living organisms. Part indeed of the opposition to Pasteur's views was due to the fact that this distinction between organized and unorganized ferments was not at the time clearly drawn. Perhaps, indeed, we are as yet by no means out of the woods. In the course of his work on fermentation, Pasteur made an important theoretical step by distinguishing the microorganisms which require the presence of free oxygen from forms which are able to live apart from free oxygen, obtaining what they require by splitting up oxygen-containing compounds in the surrounding medium. These he termed aerobic and anaerobic, respectively. Practically, this piece of work immediately led to what is known as the Orléans process of making vinegar. Some years later, after he had returned to Paris, he followed this up by his studies on wine, in the course of which he tracked various wine diseases to their sources and showed how deterioration might be prevented by raising the wine for a minute to a temperature of 50 degrees. The wine tasters of Paris gave their verdict in his favor. The old notion of spontaneous generation still lingered in some quarters, and in 1858 Pouchet had given new life to the question by claiming before the Academy of Sciences that he had succeeded in proving the origin of microscopic organisms apart from pre-existing germs. But Pasteur knew more than Pouchet as to the insidious ways of germs. He showed the weak point of his antagonist's experiments and gained the prize offered in 1860 by the Academy for well-contrived experiments to throw new light upon the question of spontaneous generation. As everyone knows, the victory was with Pasteur, but the idea is an old and recurrent one and dies hard. Thus, not many years afterward, Pasteur and Tyndall had to fight the battle over again with Bastian. The important result of what seems at first sight an abstract discussion has been not only an increased knowledge of the distribution and dissemination of bacteria, but the establishment of the fundamental conditions and methods of experimental bacteriology. Here follows substantially the same narrative as that given by Sir J. Risdon Bennett on pages 36 to 49 of this volume. It recites how Pasteur devised preventatives for the disease which was destroying the silkworms, preventatives for splenic fever or anthrax. Opposition was an ever-recurrent factor in Pasteur's life. He had to fight for his crystallographic and chemical theories, and for his fermentation theory. He had to fight against the theory of spontaneous generation, and for his practice of inoculating as a preventative against splenic fever. He had to fight for each step. But no part of his work has met with so much opposition and adverse criticism as that concerning hydrophobia, though it is easy to exaggerate the importance of the discussion, in which Pasteur himself took little part. Feeling ran high in this country. Hence, when it was announced that Pasteur, surely best qualified to speak, was to write the article Hydrophobia in Chambers' Encyclopedia, a shower of letters inundated the office. Hence, the article in question includes an editorially demanded summary of the grounds of the opposition by one of ourselves, and to which therefore we may refer the reader. While avoiding controversy and partisanship as far as may be, the question remains, what did Pasteur do in regard to hydrophobia? His claims are to have proved, first of all, that the disease was particularly associated with the nervous system. The virus is usually spread through the saliva, but it is not found in the blood or lymph, and it has its special seat in the nerves, brain, and spinal cord. Secondly, he showed that the virus might be attenuated in its virulence. The spinal cord of a rabbit which has died of rabies is, when fresh, powerfully virulent, but when exposed for a couple of weeks to dry air at a constant temperature of 23 to 24 degrees Celsius, it loses its virulence. Thirdly, he showed that inoculation with the attenuated virus rendered an animal immune from infection with rabies. To make the animal immune, it has first to be inoculated with infected spinal cord 14 days old, then with that of 13 days, and so on till inoculation with almost freshly infected spinal cord is possible. In this way, the animal becomes refractory to the infection, and if it be bitten, it will not die. Fourthly, he showed that even if the organism had been bitten, it was still possible to save it, unless the wounds were near the head, that is, within close wound, say on hand or leg, the virus takes some considerable time to spread, and during this period of spreading and incubation, it is possible to forestall the virus by inoculation with that which has been attenuated. In this case, there is obvious truth in the proverb, "He gives twice, who gives quickly." And the outcome was that while out of 100 persons bitten, 19 or 20 will in ordinary circumstances die, the mortality among cases treated at the Pasteur Institute has fallen to less than 1 to 2%. According to another set of statistics, a mortality of 40% has been reduced to 1.3%, and of 1,673 patients treated by Pasteur's method, only 13 died. As to the adverse criticism of Pasteur's inoculation against rabies, it consists, first and second, of the general argument of the anti-vaccinationists, and thirdly, of specific objections. To the two former, the school of Pasteur, of course, replies that the value of human life answers the one, and that the results of experience the other, but on these controversies we cannot enter here. The main specific objections we take to be three: that as the microorganism of rabies has not really been seen, the theory and practice of Pasteur's anti-rabic method lack that stability which is desirable, that the statistics in favor of the Pasteur procedure have been insufficiently criticized, that there have been failures and casualties, sometimes of a tragic nature. In regard to this last point, that deaths have occurred as the result of the supposed cure instead of from the original infection, we may note was admitted by the English Investigation Committee 1887, while on the other hand Dr. Armand Ruffer, who speaks with much authority, denies with all deliberateness that there is any known case in which death followed as the result of Pasteur's treatment. Microscopic verification is, of course, most desirable, and statistics are proverbially difficult to criticism. But on the whole, we think it likely that those who, like ourselves, are not medical experts, will incline to believe that Sir James Paget, Dr. Lauder Brunton, Professor George Fleming, Sir Joseph Lister, Dr. Richard Quain, Sir Henry Roscoe, and Professor Burdon Sanderson must have had grounds for saying, in the report which they presented to Parliament in 1887, "It may, hence, be deemed certain that Monsieur Pasteur has discovered a method of protection from rabies comparable with that which vaccination affords against infection from smallpox." So far a summary of Pasteur's personal life and scientific work, but is it not possible to make a more general and rational estimate of these? So much was his life centered in Paris that most people are probably accustomed to think of him as a townsman. But it is more biologically accurate the rustic, sprung from a strong, thrifty stock of mountain peasants. Nor can his rustic early environment of tanyard and farm, of village and countryside, be overlooked as a factor in developing that practical sense and economic insight which was so conspicuous in his life work. The tanner's son becomes the specialist in fermentation. The country boy is never throughout his life beyond hail of the poultry yard and the farmsteading, the wine press and the silk nursery. Brought up in the rural French atmosphere of careful thrift and minute economies, all centered not round the mechanism or exchange of town industries, but round the actual maintenance of human and organic life, he becomes a great life-saver in his generation. In short, as we might almost diagrammatically sum it up, the shrewd, minutely careful, yet inquiring rustic, eager to understand and then to improve what he sees, passes in an ever-widening spiral from his rural center upward, from tan-pit to vat and vintage, from manure heaps, earthworms and water supply to the problems of civic sanitation. The rustic tragedies of the dead cow and the mad dog excite the explanation and suggest the prevention of these diseases. From the poisoning of rats and mice, he passes to suggestive experiments as to the rabbit pest of Australia, and so in other cases from beast to man, from village to state. And on each radius on which he paused, he left either a method or a clue, and set some other inquirer at work. On each radius of work he has left his disciples, for he founded not only an institute, but a living school, or indeed whole schools of workers. We think of him, then, not only as examples in science of the rustic thinker, a type of thinker too rare in our mechanical and urban generation, yet for whom the next generation waits. As to his actual legacy to the world, let us sum it up briefly. There is the impulse which he gave, after the successful organization of his own institute, to the establishment in other countries of similar laboratories of preventative medicine, and, one may also say, of experimental evolution. There is his educative work at Strasbourg and Lille, at the École Normale and at the Sorbonne, and, above all, in the smaller yet worldwide circle of his immediate disciples. To general biology, his chief contribution has been the demonstration of the part which bacteria play, not only in pathological and physiological processes, but in the wider drama of evolution. In physiological processes, but in the wider drama of evolution. To the chemist, he has given a new theory of fermentation. To the physician, many a suggestive lesson in the etiology, inquiry into the causes, of diseases, and a series of bold experiments in preventative and curative inoculation, of which Roux's treatment of diphtheria and Professor Fraser's new remedy for snakebite are examples at present before the public. To the surgeon, a stable foundation, as Lister acknowledged, for antiseptic treatment. To the hygienist, a multitude of practical suggestions concerning water supply and drainage, disinfection and burial. On brewer, distiller and winemaker he has forced the microscope and its results, and he has shown both agriculturist and stock breeder how some, at least, of their many more than 10 plagues may be either averted or alleviated. Pasteur and his work. Professor Geddes is Professor of Botany at University College, Dundee. He has written chapters in modern botany and many botanical articles and papers. Professor Thomson is Regius Professor of Natural History, Aberdeen University. His works include the study of animal life, outlines of zoology, the natural history of the year, and the science of life. The Evolution of Sex was written jointly by both these authors. The article from which extracts follow was published in the Contemporary Review 1895. The editor's permission to reprint is gratefully acknowledged. The Life of Louis Pasteur by Monsieur Radeau, 2 volumes, were published by McClure, Phillips and Company, New York, 1901.